Hello distinguished judges, we are the Yacaranda EV team from Universitas Gadjah Mada. Today, we invite you to look beyond the machine and into the future of student-wheeled electromobility, the Super Skip EV4. Our story began in 2013. Since then, we have evolved from a vocational research group into the overall champions of KMLE 2024. This car is not just a project, it is the culmination of a decade of racing DNA and efficiency research. For the 2026 season, our goal is surgical: to secure the top-tier ranking in static events and prove that our engineering is as reliable as it is fast. With 40 students across 7 divisions, we have built a vehicle that defines excellence.
Today's briefing will navigate through our vehicle architecture, research-driven dynamics, and the economic strategy behind the build. Let's begin with the overall vehicle overview. Behold, the Super Skip EV4. Our design language prioritizes an aggressive aerodynamic profile paired with a 40 to 60 mass distribution to ensure maximum rear traction. Form strictly follows function here.
Precision lives in the details. These drawings illustrate our tight packaging, achieving a 240 kg total mass with a center of gravity of just 283 mm, with balanced compactness with ease of service, essential for trackside reliability. Engineering excellence is nothing without financial viability. Our cost summary reveals a total cost of around $34,000.
This economic discipline, combined with our technical rigor, fuels our goal to secure 325 points in static events. We aren't just building a car, we are proposing a scalable business model for the future of racing. In vehicle dynamics, our philosophy is simple: maintain the maximum tire contact patch at all costs. We utilize a full push rod system to keep our center of gravity low while providing easy tuning access for our engineers. Tire selection was driven by TDC data. We choose the Hosier 16 by 7.5-10 LCO for its rapid thermal activation. With a 1,650 mm wheelbase, we've hit the sweet spot between agility in tight slaloms and stability in high-speed corners.
Kinematics were refined through hundreds of optimum K iterations. We achieved a minus 3.1 degree camber gain during roll, ensuring that even under extreme lateral loads, the tire remains perfectly perpendicular to the track. For our uprights, we moved beyond standard aluminum to AI 7075T6. This aircraft-grade alloy offers nearly double the yield strength of the 6061 series. FEA validation confirms a high safety margin even under 3G braking loads.
Suspension control is managed by DNM-RCP2S dampers. By matching our spring weight, 250 pounds in the front and 300 pounds in the rear, to our frequency targets, we've eliminated excessive pitchings during aggressive transitions. Finally, the steering system. We've integrated a 2U joint column to prevent intrusion during impact, while the 155 mm wheel was ergonomically mapped using RULA analysis to ensure the driver remains in total control. The aerodynamic strategy for the EV4 is defined by 3 high-performance zones. Our front wing generates 297 newtons of downforce to ensure front end bite, while the side wings and the high-element rear wing contribute 381 and 343 newtons respectively, creating a balanced and stable platform. For our airfoil configuration, we prioritize a proportional geometry that balances downforce with drag efficiency. By using these profiles, we achieve an optimized lift-to-drag ratio specifically tuned for the low-speed, high-chamber demands of the Fsm track. Our CFD simulations at 80 km per hour validate this design. The result shows a coefficient of lift that is twice as large as the coefficient of drag, achieving a CL of 2.03. This confirms that our aerodynamic surfaces are operating at peak efficiency to maximize lateral acceleration. This 3D rendering represents the final integration of our aerodynamic package. Every surface has been meticulously refined to ensure seamless airflow, resulting in the aggressive yet functional profile of the Super Skip EV4.
Our powertrain philosophy prioritizes high power density. We selected the MREX 228 MV motor, which delivers 75 kW of continuous power and 124 kW at peak, all within a compact 12.3 kg package. Its efficiency map is perfectly aligned with our target operating RPMs. To translate this torque to the ground, we utilize a 3.85 to 1 chain reduction paired with a Drexler FSAE V2 limited slip differential. The setup optimizes traction and allows the EV4 to reach a calculated top speed of 129 km per hour, ensuring we are all competitive on all track layouts. Thermal management is a key for reliability. We implemented a fan-assisted air cooling system for the motor, inverter, and battery pack. By monitoring real-time NTC sensor data, our BMS ensures all components stay within safe temperature envelopes even during the grueling endurance event. Durability meets weight reduction in our material selection. We use high-strength 4340 steel for shaft and 6061T6 aluminum for the housing. Lubrication is managed with GL5 gear oil and NLGI grade 3 grease to minimize frictional losses across the drivetrain. Our energy storage utilizes a 140S3P configuration of polycell P42B, providing a nominal 588 volt and 6.53 kilowatt-hour capacity. This high-voltage architecture allows for reduction current draw, minimizing heat generation while providing a robust 79 kilowatt output. Finally, our tractive system schematic demonstrates full compliance with safety standards from the ARS to the pre-charge and discharge circuits. Every element is designed for a fail-safe operation, ensuring maximum protection for both the driver and the vehicle's electrical integrity.
The EV4 chassis is a tubular space frame optimized for structural integrity and mass distribution. Our primary objective was to create a rigid platform that minimizes elastic deformation, ensuring our suspension geometry remains predictable under high lateral loads. We selected STKM11A steel tubing for its high yield strength and excellent manufacturability. Each tube's thickness and diameters were determined by load path analysis and rule compliance, focusing on weight reduction without sacrificing the safety cell's robustness. To validate our design, we performed extensive torsional rigidity simulations. The frame was constrained at the rear and loaded at the front to measure angular deflection, ensuring that the chassis stiffness targets are met for optimal handling performance. Safety is paramount. Impact simulations for front, side, and rear scenarios demonstrates our chassis' ability to absorb and dissipate energy effectively. This test confirmed that the EV4 exceeds FSM safety regulations for driver protection in all collision scenarios. Accuracy in manufacturing is guaranteed by our modular jigging system. This ensures that every node and suspension pickup point is perfectly aligned within a 0.5 mm tolerance, preventing any misalignment that could degrade the car's dynamic performance. Finally, we utilize GMAW welding with ER70S-6 wire for robust joint strength. Our controlled manufacturing process includes pre-weld fitment checks and post-weld inspections, resulting in the high-quality, race-ready frame you see before you today.
Moving to the cockpit, our aerodynamics design focuses on driver centricity. We've optimized the leg opening and cockpit space to ensure the driver is not just seated, but integrated into the vehicle's chassis. To ensure safety and comfort for all, we validated our design using a 95th percentile driver model. We've maintained strict helmet clearance for the main hoop and braces, exceeding the safety regulations. Precision meets comfort in our adjustable pedal box. It features a fore-aft adjustment mechanism and a dedicated heel support box, reducing driver fatigue during high G braking and acceleration. Control accessibility is paramount. We utilize brain-rich ergonomics, ensuring every critical switch is within the driver's natural line of sight and reach, allowing for instant operation without distraction. Visibility is a key performance factor. Our design eliminates blind spots, providing a wide field of vision that allows the driver to hit every apex with confidence and absolute spatial awareness.
Our braking system is engineered for 1 G of deceleration with 400 newtons of pedal force. It features a dual circuit system with OBP master cylinders and wheelwood calipers, offering a 55 to 45 adjustable bias. Safety is never a compromise. Our vehicle includes a 6-point harness and impact padding that exceeds minimum requirements, backed by a dual-circuit hydraulic fail-safe for maximum reliability. We utilize an OMP 6-point racing harness, FIA 8853 certified, attached via 5/16 of an inch bolts to the chassis. It features a single hand rod release mechanism, fully compliant with the FSA standards. For head protection, we use Converse CF45 foam. This 50 mm padding is specifically selected for its high energy absorption during impacts, providing both comfort and critical safety barrier. Finally, the driver interface. Our dashboard provides real-time data, from motor temperatures to lap time, all manageable via intuitive control right at the driver's fingertips.
Our low-voltage architecture is the brain of the car. It centralizes data from the BMS and inverter via CAN-bus, monitoring everything from cell temperatures to pedal positions in real time. To power the 25.9-volt GLV battery system, we use buck converters for a stable 5 and 12-volt rails, efficiently managing loads like cooling fans while maintaining total system protection. Our telemetry strategy combines reliability with range. We use 433 MHz HC12 modules for long-range wireless monitoring, supplemented by high-speed SD card logging for deep phosphorus analysis. To protect our data, we use shielded Cat6 SD cables to eliminate EMI. Power is delivered through low resistance Wilson cables with dash DT connectors, ensuring robust connections in racing conditions.
The Super Skip EV4 is more than just a machine. It is a meticulously integrated ecosystem where every newton of downforce and every millisecond of data works in harmony. We have honored our 13 years legacy by building a vehicle that is not only fast but surgically reliable.
We are the Yacaranda EV team, and this is our commitment to the future of electromobility. Thank you.